Welcome back all of you. So with the last lecture we have completed more or less all the required concepts for critical state soil mechanics which I planned for this particular course. That does not mean that we have completed everything related to critical state soil mechanics. There are a lot more to learn further, but what is required to start with, and for this particular course as advanced soil mechanics we have finished, and we have touched upon the stress, the plastic behavior as well as the strain. But the very next stage is what is actually needed for practicing it for solving the actual problems in geomechanics. So that part we are not getting onto in this particular course. Now based on the concepts that we have learned, we will work out some problems so that whatever concepts you have gone through, it will help you to understand better. So today we will be solving some problems which will use the concepts that we have discussed in the past few lectures. Okay, so let us move on to the first problem. The problem is soil sample was isotropically consolidated to 400 kilopascal and the initial specific volume is 2.052. So this initial specific volume corresponds to this particular isotropic consolidation. The soil was subjected to drained compression. Determine failure stresses, final specific volume and volumetric strain at failure. Critical state parameters are N0 equal to 3.25, lambda is 0.2, gamma 3.16 and m 0.94. So what has been given? There is a soil sample whose critical state parameters are known. Then we have been given with the initial state, that it has been isotropically consolidated. Now knowing the initial state and the critical state parameters, we will demonstrate, or that is what we started off with. Why do we need a critical state framework? For predicting the behavior of soil. Now what do you mean by actually prediction? We have not underlined and specifically stated what actually it is, even though we have shown the figures, we have shown from initial state how the stress path will move, how it will yield and how it will fail. We have discussed this, but then this problem is a very good demonstration of you can use critical state concept for predicting the behavior of soil, or where it will yield, where it will fail, depending upon the known initial condition, and obviously the initial condition will be known, and based on the known critical state parameters for that particular soil. That is what the question is all about. Okay. So now it is given, it is isotropically consolidated, that means it is having the maximum yield stress. So for example, if I draw Q P dash, what I mean is that this is the yield curve, this is 400. So it is already at its yield point, it is not unloaded. Unloaded means we are creating lightly over consolidated to heavily over consolidated state. Here in this case it is sheared under drained condition soon after isotropic consolidation. So that means it is a normally consolidated point, so please keep this in mind. So 400 kilopascal here, it refers to NC, normally consolidated state. So isotropically consolidated, but it is normally consolidated. Now from here, if there is a shearing which is done under, it is given drained compression. So drained compression, we know that it will move like this. So it is at a inclination of 3. This line is actually marked here, this is the one. So here I have not shown the yield curve, rather, but it will look like this. So, that is, we please keep in mind when you read the question, you should be able to visualize, or rather you should be drawing, sketching the required details. And please understand about the aspects of, there are three aspects. One is whether you have to draw it in Q P dash V ln P dash, it is better you draw it on both, because that will give you additional understanding. Second thing is the effective stress path, how it will be for whether it is drained or undrained. Placing of the yield curve. Now, for all practical purpose, let us consider modified camp clay, and hence you can draw an ellipse. So, half ellipse you can draw, so that will give the entire picture of that particular problem. So, P dash F can be directly determined knowing 3 P naught dash by 3 minus M. Refer back to the lectures for knowing this. This expression has come from the geometry of the figure, because you know QF is equal to M into P dash F, and P naught dash P dash F, this is a triangle. So, one can get from the geometry of the figure P dash F is equal to 3 P naught dash by 3 minus M. So, everything is known, P naught dash is known, M is known. So, P dash F is known. So, if you substitute 3 into P naught dash is 400 here, 3 minus M is given as 0.94. So, if you substitute, we will get P dash F is equal to 583 kilopascal. Now, once you know P dash F, we can obtain QF, because we know the relationship QF is equal to M into P dash F. So, substitute for P dash F, we will get QF is equal to 0.94 into 583. So, that will give 548 kilopascal. So, what has been asked? Determine the failure stresses. So, one part is over. Failure stresses can be obtained based on the critical state framework. Then we also have the relationship Vf is equal to gamma minus lambda ln P dash F. Vf is the final specific volume at failure. Gamma is given, lambda is given, P dash F we have already determined. So, substituting, we have Vf is equal to 3.16, that is gamma, minus 0.2 is lambda, ln 583, P dash F is 583. So, that will give 3.16 minus 0.2 ln 583, which is equal to 1.89. So, Vf is equal to 1.89. Initial specific volume is given 2.052. So, you can see that it is a drained compression, and hence the specific volume will reduce. So, it has come to 1.89. So, the final specific volume has been determined. Now, what is the volumetric strain at failure? At failure, the volumetric strain epsilon Vf is equal to minus of delta V upon V naught. So, what is this? Change in void ratio, change in specific volume upon initial specific volume. Initial specific volume is given 2.052. Delta V can be determined because the final one is known. So, 2.052 is the initial minus final, that will give the change in specific volume. So, here it is final minus initial, 1.89 minus 2.052, and the initial specific volume 2.052 into 100. So, that will give 7.9 percentage. So, that is the volumetric strain at failure. So, this how we can use a very simple example of how we can use the critical state framework for predicting the final conditions, and here the conditions can be failure condition or maybe final specific volume. Now, here it is the case of drained compression. So, we know that it undergoes volume change, and initial specific volume will be different from the final specific volume. Okay. So, let us move to the next example. Soil sample A was isotropically consolidated to 400 kilopascal, and the initial specific volume is 2.052. So, sample A is that from the previous discussion we know that this is a normally consolidated state. Soil sample B was isotropically consolidated to 863 kilopascal, and then it is allowed to swell to 40 kilopascal, where the specific volume is again 2.052. Please note here, sample B has been subjected to a very high stress 863. It is allowed to swell to a very low stress, say 40 kilopascal. So, without looking at anywhere, you can see that this particular soil sample B will be heavily over consolidated. There is no doubt about it. Determine failure stresses, final pore water pressure for both samples for undrained shearing. So, now earlier example was drained shearing, here we have undrained shearing. Along with that, we have both the samples NC and OC. Now, very important aspect which you have to keep in mind is that the initial specific volume of both the samples are same, sample A and sample B, which is 2.052. Critical state parameters are same for both the samples, lambda equal to 0.2, gamma 3.16 and m equal to 0.94. Now, the very first condition which what we know is that it is undrained. So, the initial specific volume will be same as final specific volume. So, V naught is equal to Vf, which is equal to 2.052 for both samples A and B. So, this both samples 2.052 initial condition means it gives us a lot of clue about how this test would take place. And that is the beauty of the idealized critical state. We will see how. Both samples A and B would fail at the same point on critical state line. How? If you have understood the critical state concept clearly, this sentence it is not very difficult to understand. But for that it is always better that we sketch the diagram. So, it is Q P dash, V P dash. The first sample is 400. So, now this is a normally consolidated point. So, this is the starting point. So, this is the required point. Now, the next sample it has been unloaded to 40 kilopascal from 863. So, for us loading to 863 is not very important, it will be somewhere down and from there it will be unloaded so that it reaches the final state of on the unloading curve. So, this unloading curve comes from somewhere down. So, I am not drawing it here, but we need to understand that. So, here along the 40 kilopascal we know that the initial specific volume is 2.052. So, whatever is the specific volume for NC, the same should be the specific volume for HOC as well. So, somewhere here, so 2.052. So, it will be somewhere in this line. Now, we know that this is an undrained, test. So, there is no change in the specific volume. So, initial equal to final. So, the path will move in this direction and fail on the critical state line. Now, the same horizontal line will be the HOC response also. You can see that this is the starting point of HOC. So, this is HOC and this is NCL. Now, this is in the same horizontal line. So, it will fail at this particular point, and that is what is meant by both samples A and B would fail at the same point on critical state line. Why it is so? It is so because the starting specific volume is same for both the samples, which is equal to 2.052. Here the failure stress will also be same. So, this is the failure stress P dash F. So, P dash F is the failure stress, that also remains same. If P dash F is same, then QF is same for both the samples, and it is all possible because we know that the initial specific volume is same. QF, P dash F, it is all same for both. Now, here this is the kind of effective stress path for sample A, and what will be the sample B? See, if we do not know the concept of yielding, what we will do is we will draw something like this. This is also possible, or it will be drawn like this, but now we know that it has to yield before it has to fail. So, with that understanding, and we know that this is an undrained shearing, so A will be equal to 1/3 till it yields. So, it is all possible and it is in this direction because we know the concept. So, that is the point of yielding. I am not showing the yield curve here separately. So, yielding has happened, but it comes and fails at the same point. Now, we are asked to find out the final pore water pressure as well, and for that any stress condition on the TSP minus the homologous condition on ESP will give us the excess pore water pressure even at failure or even at whatever the yield point of wherever we need, we will get that. For example, in this particular case, let us say this is ESP and this is TSP. Now, if I draw a horizontal line, this point and this point, they are called homologous points. So, the difference between this will give the UXS. This is the pore water pressure. So, that is what we need to find out, and hence we need to have the total stress path, and it is very clear total stress path will be at an inclination of 3 or slope of 3, that also we know. So, at both the initial points at 400 as well as 40, we need to find out the final pore water pressure. Now, here this difference, this is the failure point. So, from here this difference will give UF of A, that is the final pore water pressure of the sample A. I cannot mark for B because it is very clumsy, but it is already discussed in the lecture. It is the point between this and this, if you draw a horizontal line. So, it will be this total minus effective. So, again the same like what we have for UFA. Okay, so if that is the case, we have the expression Vf is equal to gamma minus lambda ln p dash f, and we also know Vf is equal to V naught. Unless we know these conditions, it will be difficult to solve this problem. So, substituting the initial specific volume for Vf, we have 2.052 equal to 3.16, which is gamma minus 0.2 ln p dash f. So, from this the unknown is p dash f, we can get the value of p dash f is equal to 255 kilopascal, m is Qf is equal to m into p dash f, substitute, get the answer Qf is equal to 239 kilopascal, straightforward. So, we have determined the failure stresses. Now, we are left with final pore water pressure at failure. So, UFA is equal to PFA minus P dash F. So, we need to determine what is PFA. Now, PFA is this, that is the point. So, this is the point which we need to find out. So, what is PFA? So, PFA is equal to 400, that is from here to here is 400, plus from the geometry of the figure we can get QF by 3. So, 400 plus QF by 3, QF is known. So, substituting for QF, 400 plus 239 by 3, that will give PFA equal to 480 kilopascal. So, once we know PFA, we know P dash F, so UFA can be determined. So, UFA is equal to 480 minus 255, that is equal to 225 kilopascal, which is positive excess pore water pressure at failure. Same is the case with PFB, it is 40 plus this QF divided by 3. So, 40 plus 239 by 3, that will give 120 kilopascal. So, we have UFB is equal to same total minus effective. So, PFB minus P dash F. So, PFB is equal to 120 minus P dash F 255, that is equal to UFB equal to minus 135 kilopascal, and this is very correct because it is an HOC. So, the final pore water pressure will be negative. So, that is exactly what we are getting, and that is equal to minus 135 kilopascal. So, we have in the previous problem we predicted final condition of the specific volume, volumetric strain and the failure stresses. So, in this problem, since it is an undrained test, we have determined the failure stresses as well as the final excess pore water pressure. So, we should keep in mind using critical state concept, we can even determine the pore water pressure at failure, at yield, or at any point, intermittent point from the starting to the failure. So, these are all possible provided we follow critical state framework, we know critical state parameters, and we know what is the initial state of the sample. So, let us move on. Now, most of the things have been covered. Now, what is not covered? We can see we have not determined the yield conditions. So, now we will demonstrate a problem wherein we try to determine the yielding. So, soil sample was isotropically consolidated under a cell pressure of 300 kilopascal, and it is unloaded to a mean effective stress of 200 kilopascal. So, now from the question itself we can make out it is not a normally consolidated, it can be LOC or HOC. Drained shearing was performed, so volume change is going to take place. Determine principal stresses at yield. So, we need to understand what is yield, at what point it will yield, and we need to find out what are the principal stresses. It is not Q and P dash. It is principal stresses at yield. Now, for finding out principal stresses at yield, we need to determine what is the Q and P dash value at yield. Deviator and mean stresses at failure, that is QF and P dash F. The conditions are initial void ratio is 1.1. Now, initial void ratio of 1.1 means it corresponds to the unloaded portion, it is not the isotropically consolidated, it is unloaded now. So, 1.1 corresponds to unloaded portion. Critical friction angle is given 30 degrees. Slope of NCL in E ln P dash is given as lambda, which is 0.3. So, here we need to understand that lambda or kappa is the slope that we know that corresponds to either NCL or the unloading reloading line. Now, we have discussed most of the things in terms of specific volume and P dash, but we can the same thing can be plotted in E versus P dash. Only thing is there will be the scale difference of 1 plus E. So, here please note in the question it is given lambda and kappa corresponds to the slope in E ln P dash plot. So, you can go ahead with y axis taken as E instead of specific volume V. So, I would just like to show you this as well. So, you need to see the question properly, and lambda and kappa do not go by that blind understanding that it is always related with specific volume V. No, whatever is the slope, if it is defined in the question, lambda corresponds to this, please go ahead with that. The slope of the unloading line is 0.05. So, all the details are given. So, M we know that it is 6 sin phi dash upon 3 minus sin phi dash. Now, here the critical friction angle is already given, and that is equal to 30 degrees. If you substitute, we will get M the value to be 1.2. So, that is known. P dash C, what is P dash C? We need to understand here the significance of P dash C. P dash C is the maximum isotropic consolidation. So, that is the maximum yield stress or pre-consolidation pressure. We need to understand that it is the extreme point of the major axis of the ellipse. It is unloaded to 200 kilopascal. OCR is P dash C upon P naught dash, 300 by 200, which is equal to 1.5. Less than 2, we can consider this to be a lightly over consolidated sample. So, it is an LOC. So, this is what it means. So, this is the yield curve, ellipse yield curve for modified cam clay. So, this is the extreme yield stress or the pre-consolidation pressure 300, unloaded to 200, then it is subjected to drain shearing. So, this the effective stress path fails at point F. So, this is the point of interest to us because we need to determine principal stresses at yield. So, this Qy and P naught dash y we need to determine. So, same thing is shown here. This corresponds to 300. Here is the unloaded point 200, and this is the point where the unloading line crosses the critical state, and according to the definition of MCCM and the elliptical yield curve, we know that this is the midpoint. So, now we do not have the gamma parameter given. So, we can compute gamma parameter, rather in this case it is E gamma. So, E gamma is given, the expression we have already derived, please look back, you will find in the lecture that we have derived this particular equation. So, it is E naught plus lambda minus kappa ln p dash y by 2 plus kappa ln p naught dash. P naught dash is the initial, P dash y is the yield stress or pre-consolidation pressure, lambda is given, kappa is given, E naught is given, the initial void ratio is 1.1. So, we can determine E gamma, which is necessary for solving the failure condition. E gamma substituting 1.1 plus 0.3 minus 0.05 ln 300 by 2. So, this P dash y 300 plus 0.05 into ln 200. This will give E gamma is equal to 2.62. So, now we can determine the yield condition. We know that the effective stress path meets the yield curve at this particular point. So, we can always substitute Qy and P naught dash y in the elliptical yield curve equation. So, P dash square minus P dash y plus Q square by M square is the equation of the ellipse. Now, here P dash y is given, which is 300, P dash is equal to P naught dash y and Q equal to Qy. So, if you substitute this here, it will look like this, M the value is known. So, it will be P naught dash y square minus P naught dash y into 300 plus Qy square by 1.2 square equal to 0. So, Qy from the geometry we know that it is 3 into P naught dash y minus 200. So, it is just follow the geometry, if you drop here, that is what you will get. Substituting for Qy, so then the only unknown will be P naught dash y. So, P naught dash y square minus this, so we have substituted for Q. So, that is 3 P naught dash y minus 600 the whole square. Again expanding, we will be left with a quadratic equation. So, here we will have two roots for P naught dash y, that will be given as P naught dash y, the one of the root for the P naught dash y is 246.1, and if you substitute for Qy will be 138.2, because if you substitute for P naught dash y here, you will get Qy as 138.2. The another root of P naught dash y is 140.1 and Qy is minus 179.6. Now, Qy equal to minus 179.6 is not possible, rather it is not useful for us because it is a compression test. We know that it is a compression test and hence there is no possibility of Qy achieving a negative value. So, even though the root is there, that is not the useful term that we have to use. So, we will go with the final value of P naught dash y and Qy equal to 246.1, 138.2 is the required yield stresses. Now, we can easily find out the principal stress at failure. Why? Because P naught dash y and Qy is known, substitute the expression. So, principal stresses at yield condition we have determined. This will give sigma 1 dash y plus 2 sigma 3 dash y by 3 equal to 246.1. Also, sigma dash 1 y minus sigma dash 3 y equal to 138.2. Solving these two, we will get sigma dash 3 y equal to 200, sigma dash 1 y equal to 338.2, which is the required solution. So, this is the required solution for principal stresses. Please add kilopascal and kilopascal in the final answer. So, that is what we need. Now, the failure condition, we are asked to find out the Qf and P dash f, which we already know. So, it is the same solution, P dash f equal to 333.3 and Q is 400 kilopascal. So, both we have found out. Okay, so now we have completed more or less the predictions of stresses. Now, we also have found out we can obtain the stiffness from the critical state framework. We can also determine the strain from the critical state framework. So, we will do a problem which will demonstrate that particular aspect. Soil sample was isotropically consolidated to mean effective stress of 225 kilopascal. The sample was unloaded to mean effective stress of 150 kilopascal. The initial void ratio E naught at 150 kilopascal is 1.4. So, the initial void ratio is given. Determine total volumetric and deviatoric strain for an increase in deviatoric stress of 12 kilopascal after initial yield under drained condition. So, what we know is that it is loaded to a maximum or the pre-consolidation pressure of 225 kilopascal. Now, there is a elliptical yield curve corresponding to this, and the maximum or the major major axis of the ellipse will be 225 kilopascal. It is unloaded to 150 kilopascal and the initial void ratio is given. Now, what is asked? We need to find out what is the total volumetric strain and deviatoric strain for this given problem when the effective stress path moves beyond the initial yield curve, and that how much it is given? It is given there is an increase in deviatoric stress of 12 kilopascal. So, when the deviatoric stress moves 12 kilopascal from the initial yield curve, I mean to say the effective stress path, what will be the total volumetric and deviatoric strain? So, we need to count from the initial point to the point where effective stress path goes past beyond the initial yield curve when by an increment in deviatoric stress by 12 kilopascal. So, you will come to know better when we show it on the on a diagram. Slope of NCL in E, L and P dash, lambda is given 0.16, slope of unloading line is 0.05, critical friction angle is 25.5 degrees, Poisson's ratio is 0.3. So, now we need to use the stiffness concept, we need to use the strain concept. M, we can find out, there is no need for explanation. If you substitute sin 25.5, we will get it to be 1. OCR is P dash C 220 by P naught dash, 225 by 150, 1.5, it is an LOC problem. Yield condition. So, we need to have the yield first. We will come to the figure a bit later. Let us first resolve what is yield, yield of the effective stress path. So, what I mean to say is, this is Q P dash, we have 225. So, once we have 225, we can always draw the yield curve and then it is unloaded to 150. So, here this is the point which I want to say, and when there is a drained shearing, so we need to obtain, since it is given total volumetric and deviatoric. So, if you want to have volumetric strain, it is understood that it has to be drained. So, here this is the ESP. Now, this is the point which we are talking about where we need to find out QY and this is P naught dash Y. So, this is what we need to determine, and that we have already shown it in the last problem. So, just substitute it for P naught dash Y square minus P naught dash Y into P dash Y is 225 because this is the yield curve which it corresponds to. So, P dash Y equal to 225 plus QY square upon 1 square which is equal to 0, and QY is equal to 3 into P naught dash Y minus 150. So, it is the same as the last problem. So, solving this we can get P naught dash Y equal to 180 kilopascal and QY equal to 90 kilopascal. So, to be very precise, this is, if I draw it again on a bigger scale, this is 150, this is set at 3. So, P naught dash Y is equal to 180 and QY equal to 90. Now, we are asked if it moves past, if this effective stress path moves by this is 12 kilopascal, deviatoric stress is 12 kilopascal. So, this is the point which it corresponds to. When it deviates by this, what will be the kind of strain, total strain that it has undergone. So, this will include the strain due to this elastic portion and the strain due to this increment. So, both we need to find out. So, that is what we will solve now. So, first let us do the elastic strain determination. So, epsilon p dash e, we have already derived this. Please refer back strain from critical state, that particular lecture, wherein it is clearly given E epsilon delta epsilon p dash e, that means the elastic part of the volumetric strain, and for the initial yield we do not have any plastic strain. Till it reaches the yield point, it exhibits completely a volumetric elastic strain. So, that is what we have found out here, that is delta epsilon p dash e is equal to kappa by 1 plus E naught ln p naught dash y upon p naught dash. All these parameters, everything is known. So, just substitute, get the answer, that is 38 into 10 raised to minus 4 is the elastic volumetric strain when the effective stress path moves from the initial point to the first yielding, and epsilon q e, that is the deviatoric elastic deviatoric strain, is delta q upon 3 g. Now, what is delta q? And that is for g we need to find out, we have the expression for g, please refer back to the lecture. It is 3 p dash 1 plus E naught 1 minus 2 mu upon 2 k 1 plus mu, mu is the Poisson's ratio, E naught is known. P dash, please remember here, since it is a line starting from q equal to 0 to q equal to qy, better to take the average of the stresses corresponding to this, that is p dash will be the average value. So, p dash is equal to p naught dash y plus p naught dash, that is the initial value plus the yield value, that average we will take. So, that is equal to 180 plus 150 upon 2. So, that will give us 165 kilopascal. So, instead of using 180, use the average stress condition. So, that will give G is equal to 3 into 165 plus, you are just substituting it in the G expression, 3 into 165, 1 plus 1.4, 1 minus 2 into 0.3 divided by 2 into 0.05 into 1 plus 0.3. That will give 3655 kilopascal. So, then we can find out what is the deviatoric elastic strain till the first yield point, that is delta q upon 3 g. Delta q is 90 minus 0 by 3 into 3655. So, that will give 82 into 10 raised to minus 4. So, both the elastic strain, deviatoric and volumetric, till the first yield we have determined. I mean to say, the first yield means q p dash, when the effective stress path starts from here. So, this is the first yield. So, by the time it reaches here, what is from here, from this, for this stretch, what is the elastic strain it has undergone, both volumetric and deviatoric strain we have determined. Now, we need to determine the strain for expanded yield surface, or when the effective stress path crosses the first yield point, then we have both means plastic strain as well as elastic strain. Now, this is an elastoplastic response. It has yielded at the first yield point, it is moving by 12 kilopascal of deviatoric stress. So, delta q is 12 kilopascal given. Delta q upon delta p dash is equal to 3, because we need to find out if delta q is equal to 12 kilopascal, what will be delta p dash. So, delta p dash is equal to delta q by 3, that is equal to 12 by 3, which is equal to 4 kilopascal. So, delta p dash is known. Now, this is the final form of the figure. So, this is our initial, the green one is our initial yield curve, and that is p dash y. So, we have already done. Now, effective stress path moves from p naught dash, this is the first yield point, the conditions we have, everything it is clear. Now, it expands from A to B because there is an increment of delta Q equal to 12. Now, corresponding increment in delta P dash for this point B is known, which is 4 kilopascal. And now we need to find out this particular point, what is the maximum yield stress corresponding to the expanded yield curve. Remember, the soil sample has not failed, it is intermittent. So, this is an intermittent yield circle. The same thing is shown, please refer back to the lecture for more explanation. Now, the total volumetric strain, which is inclusive of both elastic as well as plastic, is given. So, we have already derived this, we know this how to obtain delta epsilon P dash is equal to 1 by 1 plus E naught. Please refer back to the lecture again. Lambda minus kappa ln P dash yc upon P dash y plus kappa ln P dash b upon P dash a. Now, what is P dash yc? P dash yc is the extreme maximum yield or pre-consolidation pressure. P dash y is the previous pre-consolidation pressure. P dash b is the new stress state, that is after yielding, and P dash a is the initial yielding. So, all these characteristics we need to know, we need to find out. P dash b is known, P dash a is known, P dash yc is not known. So, we need to find out P dash yc. Now, for that QA is known 90 kilopascal, QB is 90 plus 12 102 kilopascal, it is all given. P dash A equal to 180 kilopascal, P dash B is 180 plus 4, which comes from here 184, so 184 kilopascal. So, what is the stress state of B is now known. So, P dash B is known, P dash A is known, P dash Y is known, P dash Y equal to 225 kilopascal, which is the maximum yield. Now, if we substitute that in the, if we substitute for the bigger yield curve, so what we can write is P dash B square. So, this is any point within the yield. So, that is P dash B square minus P dash B. Why it is valid? Because the effective stress path is meeting at the point B. So, P dash B square minus P dash B into P dash YC, because the extreme yield point, QB square upon M square. So, QB is known, P dash B is known, only unknown is P dash YC. So, if you solve this, if you substitute for P dash B 184, this QB 102, we will get P dash YC, which is equal to 240.5 kilopascal. So, P dash YC, so all what is needed for delta epsilon P dash is now determined. So, just we need to substitute these values in this equation. Once we substitute it, we will get delta epsilon P dash equal to 35 into 10 raised to minus 4. Please remember here, this is the total volumetric strain when the effective stress path moves from A to B, and this is inclusive of both elastic and plastic strain, only for that incremental portion. Now, we need to find out the Q component, that is epsilon Q. What is the epsilon Q when it moves? So, both elastic as well as plastic we need to understand. So, epsilon P dash P is equal to lambda minus K upon 1 plus E naught, that is the plastic part of this volumetric strain. That also we have, please refer back and you will see that we have obtained this expression. So, we just need to substitute it here, all the parameters are known. So, that will give epsilon P dash P is equal to 31 into 10 raised to minus 4. Please substitute and you can see for yourself. So, we have determined the total volumetric strain for the incremental portion. Knowing that, we have determined what is the plastic volumetric strain for the incremental portion. Now, we are left with deviatoric stress. So, epsilon QP upon epsilon P dash P is equal to 2 eta upon m square minus eta square. So, this also we know, please refer back. So, eta is equal to QB upon P dash B, because we are considering the point B. So, that the stress ratio is 102 upon 184, which is equal to 0.554. M is known, substitute this, we will get the ratio equal to 1.6. So, d epsilon QP, that is d epsilon QP or delta epsilon QP, this parameter is known. Why? Because d epsilon P dash P is already known. So, knowing that, we can get it is 1.6 into 31 into 10 raised to minus 4, because d epsilon P dash P is 31 into 10 raised to minus 4. So, that will give d epsilon Q P equal to 50 into 10 raised to minus 4. Please remember, we have obtained the plastic part of the deviatoric strain, that is d epsilon Q P, which is equal to 50 into 10 raised to minus 4. We need to obtain the elastic part of the deviatoric strain for the incremental portion of A to B. So, assuming G to be constant for the stress increment, that is from A to B, we can write delta epsilon Q E is equal to delta Q upon 3 G. Now, what is delta Q? Delta Q is 12, because it is incremented by 12 by 3 into 3655, that will give 11 into 10 raised to minus 4. So, all what is needed we have computed now. So, total volumetric strain, that is from the initial point to the point B, is epsilon delta epsilon P dash is equal to delta epsilon P dash E, that is from the starting point to the point A, plus delta epsilon P dash, which is the total volumetric strain, both elastic as well as plastic. It is inclusive for the volumetric strain up to the point from A to B. So, all these parameters are known, that is 38 plus 35 into 10 raised to minus 4. So, that will give 73 into 10 raised to minus 4. Now, total shear strain is equal to delta epsilon Q plus, which is equal to delta epsilon Q E plus delta epsilon Q P. Now, the plastic portion comes only from for the portion A to B, the remaining is elastic strain. Please note here, in this particular case we could obtain this 35 directly, but in the case of a deviatoric strain we have obtained the plastic strain and the elastic strain separately for the portion A to B. So, that is why 82 is the elastic deviatoric strain which undergoes when it starts from the initial to point A. 11 is the elastic strain which it is subjected to when it moves from A to B. So, the total elastic strain will be 82 plus 11 plus 50, 50 into 10 raised to minus 4. So, this is 82 plus 11 plus 50 into 10 raised to minus 4, that will be equal to 143 into 10 raised to minus 4. So, that is what here in this particular case this issue did not come up, because we are getting the total volumetric strain from A to B. So, it is easy there. So, here it is 143 into 10 raised to minus 4. So, all the concepts with respect to critical state we have tried to cover in these problems. I would advise you strongly to go through more such problems for practice, and that will clear all your concepts. So, that is all for this lecture. Thank you.